The problem we're going to look at today is problem 4.64 from the Fundamentals of Heat and Mass Transfer, 7th edition by Bergman and Levine. The problem is stated as follows. Consider a two-dimensional steady-state conduction in a square cross-section with the prescribed surface temperatures. We're given this schematic where we have four node points located in the middle of the domain, and we're given the wall temperatures of 50 C on the left, 200 C on the right, as well as 100 on the top and 300 on the bottom. And we're asked to do three things. The first is we need to determine the temperatures at node 1, 2, 3, and 4. And it's also asked that we estimate the midpoint temperature. For B, we're asked to reduce the mesh size by a factor of 2 and determine the corresponding nodal temperatures. And we're asked to compare the results from those with the coarser grid. And then finally for C, we're asked from the results for the finer grid, plot the 75, 150, and 250 degrees C isotherms. So to solve this problem, we're going to use the finite difference. And we'll start by laying out our nodes. So what we're given is we're given all of the surface temperatures at each wall. So as stated before, we have the temperature at the top of 100, temperature at the bottom of 300, and left and right at 50 and 200 respectively. We'll lay out what we want to find. So for problem A, we need to find the node temperatures from T1 to T4. For problem B, we need to refine the grid by 2 times and compare the results at the interior to the previous problem with the coarser grid. And then finally for problem C, we need to plot the 75, 150, and 200 degree isotherms. So our schematic is going to look like this. So for all of our internal node values, we're going to start by solving the value at that node by looking at the finite difference between all of our surrounding nodes. So we'll take the one to the north, south, east, and west, and use that to come up with an expression for each of those internal nodal points. Some assumptions that we're going to make about this problem is we're going to assume it's all 2D and steady state. We're going to assume that the thermal properties in the solid do not change with temperature. We're going to assume that we're using Dirichlet boundary conditions. So we were given fixed temperature boundary conditions. So we're going to assume that there's no heat flux through any of those boundaries. It's just a fixed temperature. And we're also going to assume that our interior cells are all at 0 degrees for our initial condition of the problem. So to start solving problem A, we're going to start by going through and solving the interior points for each temperature. And to do this, we're going to use an implicit scheme. We could also use an explicit scheme where we go through each point and prescribe a certain time step. But those usually take a little bit longer to solve since we have to iterate through multiple time steps and check the convergence. So in this case, with the implicit scheme, we can write the equation for each of the interior points. And it's going to look like Tij plus 1, which is going to be the north node point to the point that we're looking at. Tij minus 1, which is going to be the point to the south. Ti plus 1, which is going to be the east point. And Ti minus 1, which is going to be the west point. And then we'll also have our minus 4 Tij. And Tij is going to be the node that we're solving. And we'll set that all to 0 to make the energy balance. We can then take our equations for our 4 node points and put it into the system's equation. So we'll take A times B is equal to C. And you can see how that matrix is laid out here. So we could actually go through and solve this by hand because it's a pretty small matrix, but it's going to be a lot easier if we can do it using a programming software. So in this case, we're going to actually do it in MATLAB. So if we take a look at our MATLAB code here, we'll start by defining all of our boundary conditions, so all the wall temperatures that we're given. And we'll also prescribe this value for the grid size. So we'll set x equal to 4 for this first case. We'll then initialize our entire matrix or our entire setup to 0, which is going to be our initial condition. So we'll set t is equal to zeros of x comma x. So that's going to be our 4x4 grid. We can then apply the boundary conditions. So for the bottom, right, left, and top, we'll set those to the temperatures that we are given. And we're going to do a little bit of a corner correction here to make sure we're setting the values correctly. So at each of the corners, so at 1, 1, 1, 4, 4, 1, and 4, 4, we're going to set it as the average between each of the walls that is meeting at that corner point. And this will give us a little bit more accurate temperature field in our final plotting. So the next thing we'll do is we're only going to solve at the interior points since we know all the boundary conditions and they're Dirichlet, so they're fixed and they're given to us. So we'll set this parameter for the number of interior nodes, which is going to be x, which is our grid size, minus 2 for the boundary cells on each side. We can then define our coefficient matrix, which is going to be a, as well as our right side vector, which is going to be b. And we'll go ahead and loop through all of our node points to make our a and b vectors. So we have for I from 1 to n, as well as for j from 1 to n, and we'll loop through and we'll set our a and our b in this single loop. So MATLAB has its own built-in system of equation solver by just using a\b. And in this case, with a relatively small matrix, this method actually works okay. If we were doing a much larger grid, we could actually look into using something like Gauss-Seidel or TDMA, which is the Thomas algorithm, to speed up this solving of the systems of equations. So once we solve our interior points, which we define as t_interior, we can then set our entire flow field. So we'll set T, our temperature field, and add our new calculated interior values. And then we'll go ahead and display some of our values. So we'll first just display the temperature matrix in our window. And then we'll go through and calculate the midpoint temperature, which we were also asked to solve for. And then we can plot some contours. So to plot the contours, we're going to use the contour f function. And we have some additional lines of code here just to change the color bar, as well as the color map to make it look a little bit more informative. We'll go ahead and plot that now. So we can see here, this is actually our temperature field that we solved for. And we can see that it's a little bit blocky. So you can see there's big jumps and kind of some rough edges as we go through here. But this is actually going to be the solution for our first problem, problem A. So for problem B, we're actually asked to refine the grid by 2. So we're going to go by this 4x4 grid that you see on the left here that we just solved for. And we're actually going to double the amount of grid points to an 8x8 grid. And when we do that, you can see this is actually the flow field that we're going to get out of our MATLAB code. And what we can see is that all of our ISO lines are actually going to start smoothing out, and we get a much more accurate answer throughout the entire domain. This isn't asked for explicitly in the problem, but just to check and make sure that our code is converging correctly, we're going to actually refine the grid a little bit more. So in this case, we ran a 32x32 grid, and you can see we get even more smoothness out of our ISO lines, showing that our temperature field is resolving quite well. We can see in the bottom corner here where we do have high gradients of temperature, there is still a little bit of roughness in our ISO lines here, showing that we may want some additional refinement in the bottom. So the final problem that we are asked to solve is to plot some ISO lines at various points. So we're asked to plot ISO lines at 75 degrees, 150 degrees, as well as 200 degrees. And so this plot on the left, each of these ISO lines are going to correspond to those points. And if we look back at our MATLAB code here, the way that we actually did that is in our contour f function, we set T, our temperature field, and then we explicitly said we wanted contours at 75, 150, as well as 200. We then did the same thing with the color map. So we set our color map so we only have 3 colors corresponding to each of those regions. And then again, turned on our color bar to look at the problem. So for the final problem, so the last thing we're going to look at here is we're actually going to do a little bit of a bonus, and we're going to use ANSYS Fluent, which is actually a finite volume method, but it is essentially solving the same finite different equations on each of our node points. And since the finite volume method is a little bit faster than a finite element method, we can actually increase the mesh size to see when we go all the way down in resolution what our final temperature field will look like. So this simulation plot on the left here was run on a 200 by 200 mesh, and we can see what our contours look like. And we'll actually compare that to our MATLAB script with a 32 by 32 grid. And what we can see is that our MATLAB code actually did a really good job of capturing the temperature field. And this MATLAB code took about, let's say, about 2 seconds to run, while as the finite volume setup took maybe about 10 minutes with about 30 seconds of solve time. So for a simple problem like this, if we do make our own finite difference equation solver in a software like MATLAB or Python, it can be a lot faster than using a commercial off-the-shelf solver, even with all the added benefits of not having to lay out all of the numerics.